Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics courses, you're in the right spot, so go ahead and hit the subscribe button. In this video, I want to talk about some basic terminology in your initial differential equations course. First things first, what is a differential equation? So first and foremost, definition. A differential equation that I'll abbreviate as just DE. So a differential equation is an equation in which at least one derivative of an unknown function appears. Let's look at some specific examples of differential equations. Let's say I have dy dx minus xy is equal to 0. So this would be a differential equation because y would be my function of x, it's unknown, and I have a derivative of that function appears as a term within the equation. Here's another differential equation. Right. So this has two variables, x and y. Notice that I have not only the function y appears, doesn't have to, we could just have dy dx equals x, that would be a differential equation. But I have the unknown function and its derivative, and that's the most important part, is that I have the derivative of that unknown function appearing. Okay, so within the classifications of differential equations, we've got two main categories. We've got ordinary differential equations, and we've got also what are called partial differential equations. So let's go ahead and take a look at what those would be. And I'm going to use a marker that shows up a little bit better. An ordinary differential equation that I'll just abbreviate as ODE. So again, that is ordinary differential equation is a differential equation, right, in which each derivative is an ordinary derivative, meaning that the underlying unknown function is a single variable function, so y of x. A partial differential equation, so a PDE, is a differential equation in which there are partial derivatives. What that means is that the underlying unknown function has multiple variables. So that means if the underlying function has multiple variables and I've got derivatives of it, of course those derivatives are going to have to be partial derivatives. Let's take a look at some examples of both ODEs and PDEs. So let's see. Let's make a list here of some simple ordinary differential equations and some partial differential equations. Okay, for example, an ordinary differential equation could look like x dy dx x minus x squared y is equal to 0. Another ordinary differential equation, 2y double prime, right? Sometimes we use Leibniz notation, sometimes we use the prime notation. 2y double prime plus 4y prime minus 3y is equal to 0. Those would be two examples of ordinary differential equations Whether I use, again, Leibniz notation or the prime notation, those are both ordinary derivatives. A partial differential equation, for one, could look like this, which is remember that del squared is the Laplacian of the function, which consists of second order partials. Another different partial differential equation could look something like, say, du dt is equal to k d squared u, and then let's say dx squared. So this differential equation, where u is my unknown function, has partial derivatives of that, and of course in this case u, the unknown function, would be dependent on the variables x and t. And in this case up here, the unknown function f could have, say, xy, xyz, essentially multiple variables, where over here the unknown function y is just a function of x. And in your initial differential equations course, chances are if you're watching this video, you're taking a differential equations course maybe at the sophomore level of an undergraduate. You would be primarily looking at ordinary differential equations. So in your course, when you say differential equations, you are really meaning ordinary differential equations. If you're using a textbook that says, say, differential equations with boundary value problems, then at the end of your book, the boundary value problem portion is going to look at some ODE or some partial differential equations, where you'll probably use the say Fourier series to solve those. But chances are ODEs is what you're going to focus primarily on. Okay. Now, looking at these differential equations right here, there's another classification. Once I get into, say, whether it's ODEs or PDEs, we can notice that there's a difference between these in terms of this has a first derivative. This not only has a first derivative, but it also has a second derivative. So something called the order of the differential equation is a useful piece of terminology. And so let's go ahead and define the order of a differential equation. Definition. The order of a differential equation is the order of the highest derivative of the unknown function. Okay. Now, if I go back up to these previous examples, well, what's the order of each of these four differential equations? If I look at this first ODE, notice the only derivative appears right here, and this is a first order, so the order of this one would be 1. This would be a first order differential equation. If I look at the second ODE, not only do I have a first derivative, but I have a second derivative. Therefore, the order of this derivative would be 2. So this is a second order differential equation. If I go over here to the PDEs, well, remember that the Laplacian consists of the second derivative, second partial with respect to x, y, whatever variables we have that the function f is dependent on. Therefore, this would be a second order partial differential equation. Now, this one has not only a first order derivative, but it has a second order derivative of the unknown function, making this a second order partial differential equation. The next important term that you will hear in your differential equations course is a linear differential equation versus a nonlinear differential equation. Once again, if this is your first semester of differential equations, linear equations is what you are going to be primarily focusing on. So let's go ahead and distinguish between those. So definition. A linear differential equation, so a linear, again, DE, so a linear differential equation, is a differential equation of the following form. And I'm going to write this as an ODE, but the same thing would apply to PDEs. The idea is that I'm going to have terms that look like this. Actually, let me write this more generically. So I'm going to add more terms to this, but the idea is that each derivative term, right, the derivative term is not going to have a power on it. It's going to just be that term, like the first y prime, y double prime, y triple prime. The only possible coefficients that it could have would be something that is in terms of the expression x. X squared, sine of x squared plus 1. It has to have just nothing with a y in front of it. So if derivative to the first power, second derivative to the first power, and then coefficients of just expressions in x. Therefore, the rest of the terms would be, well, coefficient of the n minus first derivative would just be some expression in the variable x times the derivative of order 1 less than this one, plus all the way down to f1 of x y prime plus f naught of x y is equal to, let's say, g of x. There's no products of y's, there's no y squared, there's no y prime. Everything here can only have the following types of terms within the equation. Notice that y is to the first power, and then coefficient can just depend on x. Y prime to the first power, coefficients that just depends on x, so on and so forth. And then, of course, over here I could have just expressions in x with no y's. Of course, if there was, then I could just pull it over here and factor it out. But the idea is y's cannot be powers or products, things like that. So this would be a linear differential equation, and otherwise it's nonlinear. And of course, I'll show examples of both to illustrate the point. Linear differential equations would look like the following. And over here, let's do some nonlinear. All right. Linear differential equation could look like this. X, y prime plus y is equal to 0. There is a linear first order. There isn't, well, in fact, first order linear ordinary differential equation. As far as this definition is concerned, we're really only concerned about the linear nonlinear part. Notice that y coefficient is a 1, so it at most depends on the variable x. The y prime, which would be correspond to this term, the coefficient depends on at most the variable x. Here's another one. X squared, y double prime, minus 4y prime plus e to the x y is equal to x squared. This is another example of a linear differential equation. It's also second order, but again, related to this definition, it's linear. If I look at each term here, the isolated term on the other side just depends on x, so that corresponds to my g of x. And then if I go down the row here looking at these terms, y is to the first power, coefficient depends on x. Y prime to the first power, coefficients depend on, well, this is a constant, so there's no x, but at most x. Y double prime, coefficient depends on just x. Those are all examples of linear equations. Using multiple terms that we've used, this would be a second order linear ordinary differential equation. Now let's go to nonlinear. Well, here's an example of a nonlinear differential equation. Let's say I did y prime plus x y is equal to 0. This would be a nonlinear differential equation because if I look at the term that has a y prime, the coefficient depends on y. So this would make that a nonlinear because remember that for linear, the coefficients must depend on just x. Here's another nonlinear differential equation. Y double prime squared plus e to the xy y is equal to y squared. Right? Well, what makes this nonlinear, there's multiple things here. I've got y to a power. I've also got the coefficient of y has stuff with y in it. So again, those are all nonlinear terms. Also, this second order derivative is squared, so it's not to the first power, so that would also make that nonlinear. Again, using multiple pieces of terminology, the second equation down here, this would be a nonlinear second order ordinary differential equation, right? That's a heck of a mouthful, but it does give a lot of information to the equation itself. And all those different descriptors help in terms of narrowing down the solution technique, whether it's linear, nonlinear, first order, second order, ordinary, partial. All those things help to classify the differential equation into what would be an appropriate solution technique. Okay. A couple more terms that I want to introduce. Okay, there's two more terms I want to introduce, and I left these equations up here because these will illustrate the point. So definition. A differential equation, and it could be ordinary or partial. A differential equation is homogeneous so a homogeneous differential equation, it's not homogeneous, it's homogeneous. A differential equation is homogeneous if it has the form all right, so let's again go back to my previous expression here. Where I'm going to write this as an ordinary differential equation, but the same concept applies to a partial differential equation. Let's say I've got fn x, y, nth derivative, plus next term, plus all the way down to f1 x y prime, plus f naught y is equal to, here's what I have within my differential equation so far. Y coefficient in x, y prime coefficient in x, and then up to whatever the order of the differential equation is equal to 0. So in other words, there's no g of x. Remember in the previous definition I had a g of x there. That means that this is set equal to 0. If I put everything on the same side, every single term has either a y or a y prime or a derivative of y attached to it. Otherwise is non-homogeneous. Okay, now before I kind of talk about the ones on the bottom here, that's going to determine part of the solution technique, whether it's a homogeneous or a non-homogeneous differential equation. And a lot of times when you solve a non-homogeneous, you're going to solve the homogeneous part first, and then the non-homogeneous is going to add more terms to that solution. But again, that's something you'll talk about later. All right. Let's look at these 4 differential equations that I have on the bottom, and let's classify them as homogeneous or non-homogeneous. If I look at this differential equation right here, notice that there are 2 terms here equal to 0. All the terms have either a y or a derivative of y, therefore this one is going to be homogeneous. This one down here, I've got on the left-hand side terms that have y's or y primes. On the other side, I've got an x squared. Therefore, this one would be non-homogeneous. Over here within my nonlinear differential equations, this one right here, again, equal to 0, and every term has either a y or a y prime. Even though this is nonlinear, this is going to be a homogeneous. And then down here, I could bring that y squared over to the other side, and this would then make this a homogeneous as well, because there's no isolated term with just an x in it. Now if I want to go to, let's say, like this differential equation right here, again, just to add a variety of terms to this, this would be a nonlinear first order, ordinary, homogeneous, differential equation. Again, that is absolutely a gargantuan list of names for that, but again, all those are descriptors, which kind of gives me indication for how to solve these. Once again, thank you for watching, and please consider subscribing.